So I thought I would write down the solutions to the Chapter 4 written exam to save myself some time and also so that you would have the solutions worked out. The first question was the limit as x approaches pi of 8 cos x plus 8 divided by x minus pi squared. So since pi is in this location, -1, 0, cosine is the x coordinate, which is -1. So you would, if you plugged it in, you'd get -8 plus 8. And on the bottom, you would get pi minus pi squared. So this is of the form 0 equals 0. And so that means we can apply L'Hopital's rule. When we apply L'Hopital's rule, we take the derivative of the top, which is 8 times negative sine x. And on the bottom, we get 2 times x minus pi to the first, and then the derivative of the inside again is just 1. So just writing that a little cleaner, I'm going to make this 4, and I'm going to get minus 4 sine x over x minus pi. So again, if I am using this, we notice that the sine is 0, sine of pi is 0. So we get -4 times 0, and pi minus pi is 0, and we end up with the form 0 over 0 again. So now we have the limit as x approaches pi of, we're going to apply L'Hopital's rule again. So we're going to get -4 cosine of x over 1. And then our answer will be -4 times -1, or 4. So that's the answer for number 1. Number 2 was to graph x times the square root of x plus 7. And I did ask you to follow kind of a prescribed method of doing it. So I asked you for the domain. Well, in this case, we know that what's under the radical, x plus 7, has to be greater than or equal to 0. So x has to be greater than or equal to 7. So I would have accepted that, -7. I would have accepted that or -7 to infinity. The range is harder to find, and you'll be able to find it once you have the minimum. So we're going to have to find our minimum first to find out what that is. And then the next question was to find the x and the y intercepts. X intercepts come from setting y equal to 0. So we'll get x is 0, or the square root of x plus 7 equals 0. And we'll get 0 and -7. So we actually get 0, 0, and -7, 0. And our y-intercepts come from letting x equal 0. So we'll get 0 times the square root of 7, which of course is just 0. So we now have two ordered pairs that we can put on the graph. 0, 0, and -7, 0. those over here, just so we still have them. And then I want to move on to finding my first derivative. So again, just for reference, we have x times x plus 7 to the 1/2. So taking the derivative, we have to use the product rule. The first, the derivative of the second will be 1/2 times x plus 7 to the minus 1/2. First times the derivative of the second, plus the second times the derivative of the first, which is just 1. So this is our first derivative here. If I set this equal to 0, and I'm also going to kind of write it a little nicer. By using our fractional exponents and making them square roots. To find our critical points now, I'm going to move the root x plus 7 over to the other side. And I'm going to cross multiply. So we'll get x equals -2 times x plus 7. X equals minus 2x minus 14. 3x equals minus 14. And x equals minus 14/3. Putting this on a line chart for our first derivative, we know that the function is defined at -7, but not to the left of that. -14/3 is like -4.7. So we'll do -14/3, which is approximately -4.7. And I'm going to test something in here. Oops. I'm going to test -6, and I'm going to test -3, or let's just test 0. That's easy. So I tested in my first derivative, f prime of -6, and then also f prime at 0. It turns out that my f prime at -6 is a negative for f prime at -6, so that will be decreasing in that interval, and a positive value at f prime at 0, so that will be increasing. So we can say by the first derivative test, f of -14/3 is a local minimum, and if I plug that in, f of -14/3, we get -14 √21 over 9, which is approximately -7.13. So keep in mind, I'm plugging this into this original function up here at the top, -14/3 times -14/3 plus 7, and then the square root of that. Okay, so we have a couple more ordered pair. Oh, we have one more ordered pair, -14/3 and -14 √21 over 3. And this is a minimum. So let's go to our second derivative. The first derivative happen to be x times x plus 7 to the minus 1/2 over 2 plus x plus 7 to the 1/2. So when I take my second derivative, I'm going to use the product rule here and then just the chain rule here. So product rule is going to give me my first. The derivative of the second is minus 1/2 x plus 7 to the minus 3/2. So that's the first times the derivative of the second, plus the second times the derivative of the first, plus, and now we're taking the derivative of this, 1/2 x plus 7 to the minus 1/2. And you should notice that if you have half of something and half of something, you have one whole of that something. So we have the second derivative of x is minus x over 4 and x plus 7 to the 3/2 plus x plus 7 to the minus 1/2. So we want to find our points of consideration. So we're going to set that equal to 0, and I'm going to add this to the other side. So I'm going to get x plus 7 to the minus 1/2 equals x over 4 times x plus 7 to the 3/2. And I'm also going to cross multiply. So when I cross multiply here, we add the exponents. We're going to get 4 x plus 7 to the first, because minus 1/2 plus 3/2 is 2/2, or 1, equals x. 4x plus 28 equals x. 3x equals negative 28. X equals negative 28 thirds. Well, negative 28 thirds is less than negative 7. And if you recall, here we are at 0, or not 0. Let's make that a negative 7. Because we know our function is not defined over here. And we have no point of consideration. That means that this function is either strictly increasing or strictly decreasing, or not, excuse me, strictly concave up or concave down over here on the right. So we just have to test a value. I'm going to test 0 because it's easy. The second derivative at 0 is going to give me, and again, I'm looking right, well, I guess I'll look right here. It's going to give me 0 over 4 times 7 to the 3/2, which is just 0, plus 1 over 7 to the 1/2. So this is a positive value, this is 0. So that means that this function is always concave up. So we are ready to put this all together. There are no inflection points because we had no place where it could change concavity. And we get the following graph. We know, oh shoot, here we go. 1, 2, 3, 4, 5, 6, 7. Negative 7, 0, and 0, 0 were our x and y intercepts. We had negative 14 thirds and negative 14 times the square root of 21 over 9, which was approximately minus 4.7 minus 7.1. So 1, negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5, 6, 7. So it'll be about here. And this function decreases and then increases. And it is always concave up. So the only question we did not answer was what was the range. But now that you know that this is at negative 7.1, we can say negative 7, well actually we should do it exactly, negative 14 root 21 over 9 up to infinity. Okay, last one. The last one was to, let's see. So we wanted to find the minimum ladder that would clear a fence and go over to this house. And what we were told is that the fence was 30 feet from the house and the fence was 4 feet tall. So if that is the case, I'm going to call this X, and I'm going to call this length here Y. And I'm just going to draw this just a little bit bigger here so that we can make some comparisons. What we know is that this is perpendicular. These are both at right angles to the ground. And of course, they both triangles, this black triangle here and then the larger blue triangle, share this angle here. And then if two of the angles are the same, then the third angle has to also be the same. So basically, that black triangle and that blue triangle are similar triangles. So I'm just going to make a ratio. 4 is to X as Y is to, hopefully you're thinking, X plus 30. So if I solve for Y, I get 4 times X plus 30 over X. And that is that side there. Now what I'm looking for, drawing this one more time, we have 4x plus 30 over x, and we have x plus 30, and we're looking for the length of the ladder, which is a hypotenuse. So we're going to use, I'm just going to use L. L squared is x plus 30 squared plus 4 times x plus 30 all over x squared. And what we could do is take the square root, but then one of the things that we had done was take the radicand out of that square root. So rather than calling this L squared, let's call this L, well, hold on, just so I don't confuse anyone. This is the length of the ladder. 4 times x plus 30 over x quantity squared. This is the length of the ladder in here in blue. But what we ended up doing is taking that out of the radical and just having this radicand. And I think we called it L star or D star. So I'm going to take this red circled thing here, and I'm going to actually factor out an x plus 30 quantity squared. That's going to leave me with 1 plus 16 over x squared. Because remember, I'm applying this square to every piece. So this is what I'm trying to minimize, because if we minimize this, we minimize this length of this ladder. So at this point, what we want to do is take the derivative of this L star. So L star prime is going to be the first times the derivative of the second plus the second times the derivative of the first, which will be 2 times x plus 30. And then we have to find our critical points, and our critical points, we're going to have to set this equal to 0. So on the next page here, I'm going to rewrite this, and I'm going to write it without these negative exponents. So let me write L star prime out again. It was negative 32 x plus 30 squared over x cubed plus 2 plus 32 over x squared times x plus 30. So we need to find our critical point. So I'm going to set this equal to 0, and I'm going to go ahead and move this to the other side. So we're going to get that this piece here, 32 times x plus 30 squared over x cubed equals 2 plus 32 over x squared times x plus 30. Now we know a couple things here which allow us to clean this up pretty easily. First of all, we know that x cannot be 0, because if it were 0, and here's your fence, your ladder wouldn't even clear the fence. It would have to go like this, so it would be in front of the fence. So what I'm going to do now, because that is the case, is I'm going to multiply both sides by x cubed. So that's going to go away on this side. 32 times x plus 30 squared. On this side, I'm going to distribute it through this first set of parentheses. 2x cubed plus 32x times x plus 30. I also can divide by x plus 30 because I know x plus 30 cannot equal 0 because x cannot be negative 30. X can't be a negative number. When I look at this now, one of these is going to cancel, so that goes away, and this is going to cancel. So we have 32x plus 960 equals 2x cubed plus 32x. If I subtract 32x from each side, I get 2x cubed equals 960, or x cubed equals 480, and x is approximately 7.83. So this is a critical point. We know that our ladder has to be at least bigger than 0. Negative values aren't going to make any sense, or x values have to be at least bigger than 0. And we have a critical point of 7.83. I'm going to leave it to you as an exercise to test like 1 and 8. And it turns out that if I plug into L star prime, the derivative, that I will get a negative value here and I will get a positive value when I plug in 8. So this is in fact a minimum. F of 7.83 is a minimum. And remember, that's just our x value. This is our x value. We really want to know what is the length of the ladder. So we have to go back. Unfortunately, I can't go back on this, but I'm going to go back to my function, which was L. Let's not make it squared. Just L, which was the square root of x plus 30 squared plus 4 times 30 plus x over x squared, and we're going to plug in x equals 7.83. So this will give me 37.83 squared plus 4 times 37.83 divided by 7.83 squared, and we should get approximately 42.5 feet. So I want you to kind of look at this and go back and make sure that we went through the steps that we should have gone through. We drew a picture, and the picture served as our identifying our variables. We wrote the function that we wanted to minimize, and then we wrote it in one variable, and in this particular case that meant we used similar triangles. We found L star, which was just the radicand, and then L star prime. We found our critical points, and we verified that it was a minimum, and then lastly we answered the question. So we follow the same steps that we go through for every optimization problem. That concludes this video. Thank you.